So today is November 17th, 2011. This is AP Statistics at Berkeley High. This is the continuation in the final part of the 6-3 lecture. We start with the idea that, again, the geometric and the binomial distributions have two different settings, but they're essentially the same except for one thing. Binomial, always a set number of trials. Always try this thing n number of times and count up how many successes you have. The geometric, do as many trials as it takes until you get your first success. Only difference between the two distributions. All right? Or the two settings. Now let's talk about bits. Let's talk about the random variable x. Hello, Andrew. How are you today?
All right.
Same here. Except I have coffee. Did you get coffee?
No, I don't drink coffee.
Probably a good idea. Not to drink coffee. All right. So, the distribution that the value x, how many trials before our first success, has properties. Just like the random variable x in the binomial situation had properties. It took on the values in the binomial case from 0 to n. Geometric's different though. The geometric distribution can't take on the value 0. I can't get my first success after 0 trials. The lowest value that the geometric distribution can take on is 1. How big can the random variable x be? It could be infinite. It could be you're trying to do something and you just keep on trying and trying. So there's really no upper end to the random variable x. How many trials does it take for me to flip a coin, let it drop on the floor, and then have it stand on its edge, for example?
I don't think it ever.
You don't think it ever? So I could try and try and try and try, and it never is going to happen. Okay. So the possible values for the random variable associated with a geometric setting are from 1 to infinity. Now, like we had said before, what you're going to have in your test or on your quizzes, you're going to have a situation. And you're going to have to ask, of that situation, is it geometric or is it binomial? What's that one thing you're going to look for to try to discern one from the other? N or T. Is it a set number of trials, that's the N, or you do as many trials as it takes until you get your first success? T. Set number of trials, binomial. Try for your first success, geometric. Okay? Everyone okay with this? No questions? Next slide. All right. So let's look at an example. Okay. Have everyone read over the example? I've got somebody's birthday in my head. How many trials is it going to take for you to guess the birthday that I'm thinking of? We start with Perry. Perry's a very smart guy. Guess a birthday. May 5th. Oh. Nope. Okay, May 5th is not the answer. Hey, Nolan, you're a smart guy. Guess my birthday in my head. January 12th? Nope, not even close. Okay, keep on going.
February 6th.
Nope. Next.
July 25th.
July 20, March, April, May, June, July 25th. Nope, that's not it.
June 12th.
June 12th? Nope. Okay, let's stop this game. Okay, so what's going on here? Every single guess has a probability of success, right? 365. Actually,
No.
no, because the odds are changing every trial. After Perry guessed May 5th, guess what you're not going to guess, Abby? So the first trial was one out of 365. What about the second trial? 1 out of 364. And the third trial? 1 out of 363. Is this a geometric situation? As we just described it.
No, because of the probability of success changes.
Okay, that's the S in bits, right? S was the probability of success has to be equal. This fails a binomial, the geometric situation. Now, if the guesses were independent, if after Perry guesses, Nolan doesn't have any idea what he just guessed, and he has the possibility of guessing the same day again, would it then be geometric?
Yes.
Yes. And we might describe that geometric distribution. We may say that the geometric variable y is equal to has a geometric distribution, and we only need one number to describe the geometric distribution, and that's the probability of success. That describes the whole distribution. The probability of success is enough to describe the entire distribution. Now, can we talk about what's the probability that the first person guesses it correctly? Again, we changed the rules. Now every guess is independent of each other. No one knows what other people have guessed. One more time, Danny.
365 times 64.
Okay, I'm going to reiterate this again. As compared to the way we just did it, we're doing it a new way. Perry makes his guess. No one knows what he guesses. All right? And I say, did Perry get it right? Yes or no? What's the probability that Perry gets it right? What's the probability? 1 over 365 says Cody. Does that sound good to you? Okay. The probability it was guessed correctly on the very first trial is 1 over 365. Okay? But let's talk about this. What's the probability that it gets guessed correctly on the second trial? Remember, in the geometric situation, we can't get to the second trial unless we had a failure in the first trial. So what's the probability that the birthday is guessed correctly on the second trial? Well, what happened on the first trial? A failure. What's the probability of failure in this case? 364 out of 365. So there's your first trial and it's a failure. Then we had a success. Times 1 over 365. So there's the probability of the random variable having the value 2. Hey, what's the probability that it was done correctly on the third trial? First trial must have been a failure then, right? No? Remember, every trial is independent. No one knows what they had guessed before. First trial was a failure. Second trial was a failure too. And the third trial was a success. Now, I'm not going to do this any more times. I want to go and see if we can find out what is the general formula for finding out that the first correct guess happened on the kth try. A general formula for what's the probability that the first success happened on the kth try. Well, let's see. When we had, on the second try, we had one of those. When we had it on the third try, we had 2 of those. If we had the first success on the kth try, how many failures must we have had? K minus 1 failures? 1 fewer than K? Exactly right. 364 over 365 to the K minus 1. And then what happened right after those K minus 1 failures? We had a success. What's the probability of success in this case? 1 over 365. We have a general formula for finding out the probability of having the first success on the kth try. This is the one for the birthday problem. Here is the formula in general. If we are in a geometric distribution, the probability of having your first success on the kth try is 1 minus p, that's the probability of failure, to the K minus 1, that's how many failures we had, followed by our 1 success, P. Now, get your formula sheets out, please. Get your formula sheets out, please. There's an area where the formula for binomial stuff is. This is the one and only thing I'm going to allow you to write on your formula sheet. I'm going to let you add the geometric stuff on your formula sheet. It's not there. Okay. Find the sheet on your. Find that area in your formula sheet where it has the binomial stuff. It's on page 4. Okay. Why don't you set just to the right of it, write geometric, and I would like you to add this formula. The probability of the random variable y meaning a random variable associated with the geometric setting. The probability of y equal k is equal to 1 minus p to the k minus 1 power multiplied by p. All right? We're going to put at least 2 more formulas in this area. Are you ready to continue? Yes, that's fair. Oh, Abby, give me a thumbs up. Ready? Okay. By the way, let me just erase this for a second. Let's see what the textbook publisher had to say about this. Okay. See if we did it right. Wait, 7? What's the deal with 7?
Each trial, the probability of the perfect guess.
Why would they have it? Why would it be 7? Oh, the birth day. Oh.
Everything you just did.
No. I was looking for a birthday, as in one word, as in January 3rd. They were talking about birthday, as in, were you born on a Saturday? Were you born on a Sunday? So, okay, forget it. We're just going on.
That's weak.
Who would do that? Do you guys even know what day you were born on?
Thursday.
No?
I was born Thursday.
I was a Sunday. Okay, let's talk a little bit about the shape of the geometric distribution. The shape of the geometric distribution is always skew right. Write that in your notes, please. The shape of the geometric distribution is always skew right. It's a really strange phenomenon here, but let me say it anyway. The most probable outcome for a geometric problem, the most probable outcome is a success on the first trial. It's very contradictory. But here's the reason. On the first trial, what's the probability? Let me say it again. For success on the very first trial, what's the probability? And the answer is, if we're in this general geometric situation where the probability of success is P, the probability I get a success on the first trial is exactly P. And we know that probabilities are numbers that are between 0 and 1. Right?
What's K again?
K is is the number of trials for exactly the number of trials for success. Hey, what's the probability of a success on the second trial? It's 1 minus P times P. Wait, P is a number that's a fraction. 1 minus P is a number that is a fraction. What happens when you multiply two fractions together? What happens when you multiply 1/2 times 1/2? It gets smaller. 1/2 turns into 1/4. And you do that with any two fractions, any two numbers between 0 and 1. When you multiply a fraction by a fraction, the result is smaller than either of the two fractions. So in the second trial, 1 minus P, which is a fraction, times P, which is another fraction. You multiply them together, you get a smaller number, and the probability of the first success happening on the second trial has to be smaller than the probability of the first success on the first trial. And then, what happens when you take this number and you multiply it by another 1 minus P? That would be the probability of the success on the third trial. What happens? It gets smaller still. So the geometric distribution has this thing where it's always highest on the first trial, and then the values of that random variable just get lower and lower and lower over time. It's like, still boggles my mind. No matter what geometric setting you're in, whether it's me throwing markers into a box, which has a really high probability of happening, or you guessing exactly a particular birth date, which has a really low probability, always the highest, the most probable random value for that variable is 1. All right. Let's see what else is on this. Let's see what else is on this slide. Make sure I cover everything. Okay, heavily right skewed. Okay, the center, by the way, for this, where you have to guess the right birthday, Sunday, Saturday, whatever. The mean of this particular distribution is 7. Now, when they said birthday, they said the probability of guessing right on any individual trial is 1/7. Wait, probability was 1/7, and the expected number of guesses was 7. I wonder if that's a coincidence.
U of P equals P.
Something is going to take me. It's something like flipping a coin has a probability of 1/2 of being heads. About how many coins do I have to flip before I expect to get my first head? Probably 2. Something's got a 1 in 100 chance. About how many trials is it going to take before I hit it? Probably about 100. That leads us to the second thing that you're going to put on your formula sheet. The mean of some geometric distribution. Now, of some geometric distribution is equal to 1 over P. It's equal to the reciprocal of your probability. So if something's got a 1/4 chance of happening, about how many trials is it going to take before I get my first success? About 4. Right? So the mean of a geometric variable is 1 over P, which only leaves us with one more formula to write down. What is the standard deviation of a random geometric variable? I can't remember off the top of my head. So let me find out what it is. Let me erase that. So the standard deviation for this one is 6.48. And pretty soon, they're going to tell me the formula for that. Nope. Okay, there's the mean. We already got that down, right?
Yeah.
All right. They didn't give it.
Oh, there's those.
There is none.
Those bastardos.
What's that?
I was speaking about Italian.
Oh, you called them bastards.
Astartes. Italian. Everyone loves Rangers.
Yeah, yeah.
I don't think you said it loud enough.
Yeah, I hope not, but I said it loud enough, so. All right, so anyway, that's I don't know what the, isn't that convenient? I can't remember it, and they don't put it on there anyway. So I won't be testing you on that. All right, so here's our summary for this section. Remember, we have two general ideas in this section. Binomial and geometric, got to be able to tell them the difference. Both of them involve multiple trials. Binomial, set number of trials, count up the number of successes. Geometric, we keep on trying until we get that first success. All right? Remember that the binomial coefficient
Is something, choose something.
is n choose k. And please recall that in our calculator, that looks like n NCR k. 10 trials, choose 5. All right? And by the way, what we're going to do is we're going to take on, we're going to finish this recording, but now I'm going to also show you, embedded in the problems that we're going to do on the board right now, I'm going to show you some extra stuff on the calculator to allow you to do these calculations relatively quickly. All right? Remember that the binomial distribution has a mean of NP. The binomial distribution has a standard deviation of the square root of NP times 1 minus P. Please recall that if you have at least 10 successes expected, if you expect at least 10 failures in a binomial situation, that you may approximate the binomial distribution by using the normal distribution. That the binomial distribution with n trials and p probability of success is approximately the same as a normal distribution with a mean of np and a standard deviation of n times p times 1 minus p. And you may do that as long as you expect at least 10 failures and at least 10 successes. Sorry, 10 or more failures and 10 or more successes. Sometimes that's referred to as the rule of thumb. All right? Also in the summary, remember that the geometric setting, count the number of trials to your first success. Oh, what's wrong with, what happened to this?
Paul said a bad word and it got on the recording.
Okay. Remember that the probability of getting your first success on the kth trial is 1 minus p to the k minus 1 times p. The expected value for geometric is 1 over p. And that concludes the 6-3 recording. Now, let me close off this. Would you please get a list of... Paul. Okay, let's get... you get together what problems you want me to do from the homework.